So talking about mass spec, basically two types of versions here. You have a molecule that has lone pairs and a molecule that doesn't. And so just to bring you through the process, so the electron beam, what happens is the molecule gets one electron knocked out. And if it's a lone pair, it knocks out one of the electrons from the lone pair. If it's not, it just knocks out an electron from the molecule, basically.
Edit this right.
All right. So then once that gets knocked out, the molecule itself loses an electron in this case. So you see this like brackets and a plus charge. But for this one, you actually know where the electron got knocked out. So you draw it like that. So that first step, then now at this point, all you're thinking about is carbocation rules, right? It's carbocation stability. So if I were to number some of these atoms, 1, 2, 3, 1, 2, 3. Places I'd like to break it off, I could probably actually 4, 5, 6. I could think of places on this top molecule, right? This top molecule that would make sense. So one of those places would be between carbons 1 and 2. So if you broke that bond there, you'd want to make the most stable carbocation possible. So you put the plus charge there. And then here on 2 and 3 would be the radical. But this would be the fragment that you would see. That's just one possibility. For the bottom one, what could happen is that this bond would break, right? And both these electrons would go there. And that would give you a oxygen with not a full octet, but all its valence electrons. And again, that same tertiary carbocation, right? So these kind of like these carbocation rules. But you'd expect to see this in the mass spec. So let's take a look at just a random molecule I made up that we're going to look at analyzing both with NMR, NMR, and IR. So for NMR, we're just looking for the number of different non-equivalent, chemically non-equivalent hydrogens. So let's see if we can take a second and see if we can count those up. All right, so got some answers here. Let's go over this together. So for the NMR, I have 6 peaks. A, B, C, D, E, and F. So this molecule is not very symmetrical, right? It doesn't have a plane of symmetry. And every single one of the carbons is different too. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 peaks for the carbon. For IR, we look for OHs first. Don't see any OHs. Then we look for our types of CHs. I see sp3CHs, E and F. I see sp2CHs, D, C, and B. And I even see an SPCH, A. I have a acetyl bond O from an ester, or 1745. I have a benzene ring, 2 stretches there. I even have 2 triple bonds, nitrile and alkyne. So these are the kind of things I'm looking for. Yeah, nothing more than that. Hopefully you could go through and label where these would be at on your table. All right, we practice that quite a bit. This is the allylic region. This is like that Z region. This is on the benzene ring. This has a specific spot too. But you could find out where these peaks and these hydrogens and carbons would be at by using your tables. But just being familiar with those things. And these kind of IR stretches are the simple ones. You know, if I ask for 3, you should be able to do that pretty easily. So this is a good question, just kind of understanding when do I need water, when do I not need water. So if you just look at this, right, we talked a lot about this carbon being the carbon that's bound to oxygen twice. So like this carbon right here is this carbon. All right, so this is the spot. And if you look at what needs to happen, right? So oxygen 1, oxygen 2, oxygen 1, oxygen 2. There they are, right? And also they both have H's, so we need to add 2 H's, and then what is this? And an O. So really that kind of is the giveaway that you need to add water here. Now, I'll usually put water here and I'll say solvent so you'll know it's the thing that needs to react. And if I give you the steps as well, make sure you're following along really well on those steps, right? The protonation, the proton transfer, addition, elimination, all those kind of things. But this is a good way to kind of get a feel for what's going to happen overall, right? We talked about these are the bonds that need to break, right? We need to get those things taken off. So that's you can kind of tell how the solvent's involved. And then the reverse process of this, right? I usually, if I'm going this way, I usually have to write excess here, right? To let you know, hey, there's a lot of this alcohol around, you need to use it, right? That's the other kind of clue to think about.